Hey, it's Horner, and this is F2 for gravity and Coulombs law. We have two identical metal rods, and they each are given equal positive charges. So because they're given these positive charges, they do repel each other, and that keeps any charge from being transferred to or away from either of the rods. So student wants to determine that relationship between the electric force acting on the rods and the separation distance between the two. The student resolves to only perform experiments in which two rods are set parallel. So now that we know that they're parallel, that's good. Outline a procedure the student can follow in order to make those measurements and allow the student to determine the relationship between the electric force acting on the rods and the distance between the two. So here we've got to make sure that we're measuring distance and we're measuring force. So measuring distance, we're going to use a meter stick, measure force, a force sensor. So basically, the student here would just say, set the two rods on the table as shown so that they are parallel to each other, measure the distance between the two with a meter stick, and then attach a force sensor to the right rod, tape down the left rod, and then pull on the right rod with the force sensor until it moves. At the instant that it starts to move, you'll record that maximum force, and then you'll go back and you will set the distance a little bit further apart or closer together. Either way you go is absolutely fine. And you'll continue to do that and use 3 trials for each distance. Remember, we always have to talk about minimizing error. So if you do those things, you will get 3 points. If you go through the data analysis, now we're going to create a table to measure distance and force and those trials. From that table, we will create a graph of force versus displacement. So if we do force here and we do displacement here, we're going to see if we get a proportional relationship like this or if we get an inverse relationship like this. If we do get that inverse relationship, then when you plot f versus 1 over that distance, you should get a straight line. And those are the 2 points for part B. For part C, now they've given you an equation, and they find that equation for the force between the two rods is 2kq. Remember, q is the charge, k is a constant, r is the radius, and L is the length of each rod. So r, I guess it's not really radius, it's the separation distance. K is the Coulombs law constant, which is 9 times 10 to the 9th, and then it tells you what all the other things are. So here's their data. This, when you plot it, gives you this relationship. So you get a hyperbola, or hyperbola is what we've called it, and you know that that's inverse, and that your equation would be the force of electricity should be equal to some constant times 1 over that separation distance, 1 over r. So here it should be a relationship like that, should look like this. We plot it to see if it's similar. If it is, then we linearize that by plotting Fe versus 1 over r, and we get that straight line, and that will help us. So that is your 3 points. Now we're going to assume that those rods are cylindrical in shape and that the student holds the rods on a flat table so they're very close to each other in parallel. The student releases the rods and they push each other apart. Okay? If we assume that there's only an unbalanced force acting on the two rods, it's just the repulsion electric force, they want us to figure out, does that magnitude of the acceleration of the rod increase, decrease, or remain the same as they move away? It should decrease. So they will move away from each other. Their speed will continue to increase, but not at the same rate as you would think. So here the force is proportional to the acceleration, or acceleration is force over mass. And as the masses, or as those rods move further away, that separation increases and the force decreases, which means that your acceleration is decreasing. However, your speed will continue to increase because you still have acceleration. I liken this to, if you press all the way down on the accelerator, you accelerate a lot. If you pull back on the accelerator just a little bit, you still are going forward. You're still picking up speed, but not at the same rate, not picking up as many meters per second as you were originally. If your acceleration is in the same direction as your displacement, your speed is always changing. So that is really the answer to this one. So notice your speed and acceleration are in the same direction. If that's true, then your speed is always increasing. And that is the end of the 12-point problem, number 2.